The new section is entitled Cofactor Expansion. Cofactor expansion will allow us to do two things. It will finally allow us to calculate determinants without using a definition that are bigger than 3 by 3s. Because 2 by 2 we have a fairly straightforward technique. 3 by 3 we have a nice technique, the spaghetti method. But 4 by 4 doesn't really have a special technique other than using a definition. Same with 5 by 5, 6 by 5. And you surely don't really want to do a 10 by 10 matrix or determinant of our 10 by 10 matrix using a definition. And it also makes 3 by 3s a little bit easier, or possibly a lot easier. Cofactor expansion. So we won't do any tricks with this one. We'll just do straightforward cofactor expansion. You need to decide, and we'll talk about how to decide in a moment, but you need to decide which row or column you want to expand about. Let's suppose you want to expand about column 1. Now, just because I'm going to write on the matrix a little bit, I want to write it down a few times. Okay. So we're going to expand about the first column. So we're definitely expanding about the first column. One of the hardest things about drawing those lines is you lose the ones. And then, since we're expanding about a column, we're going to cross off row by row. First, we cross off the first row. Now, what you're going to write down now has 3 parts. It's going to have -1 to the row plus column position of the number that got crossed off, namely the 3. It's in row 1 plus it's in column 1. And it's a 3. And then you have a determinant. And the determinant is, you take the determinant of what you did not cross off, namely 4, 2, 1, 3. And then you go plus, and you cross off the second row. Since the first row is already crossed off and it's hard to see, let me come down here. I cross off the second row. But in all cases, we're expanding about the first column. So I crossed off the second row now. So I have the same 3 parts. -1 to the row plus the column. And then the number that we crossed off is 1. And then the determinant that remains. 3, 2, 1, 3. 3, 2, 1, 3. And now I cross off the third row. But again, if I cross off the third row, the second row is already crossed off. It looks complicated. So let me cross it off here. All that's crossed off is the first row, the first column, and the third row. So it's plus. That entry is -1. It's the third row, the first column. It is a 0. And what isn't crossed off are those 4 numbers. 3, 2, 4, 2. And now I do the computation. -1 to the 2. 1 plus 1 is 2. -1 to the 2 is 1. Times 3 is 3. Times that determinant. It's 4 times 3 minus 2 times 1. That's 3. -1 to the 3 is -1. Times 1 is -1. Adding a -1 is the same as taking away 1. Times the determinant. 9 minus 2. 9 minus 2 plus. Now, most of what I'm going to write, we don't have to do. 3 plus 1 is 4. Negative 1 to the 4 is a 1. Times 0 is 0. Times whatever this is 0. The fact that there was a 0 there, the fact that that number that got crossed off was 0 is very friendly. That whole mess is 0. This is 10. 3 times 10 is that number. That's 7. 1 times 7 does say minus. 1 times 7 is 7. Adding 0 don't bother. The determinant is 23. And I didn't do the spaghetti method. You may say, please, please let me do the spaghetti method. It's so much easier than what you just did. Well, after you see a few of these, it's not that bad. And yes, maybe the spaghetti method is a bit shorter. But what if you have a 4 by 4 matrix? What if you have a 5 by 5 matrix? The bottom line is at the end when I show you the tricks that you can do and use this cofactor expansion, it's even better for 3 by 3s. 2 by 2s, you're not going to improve on the 2 by 2s. You multiply those two numbers, you multiply these two numbers, you subtract, you're done. So let's do another one. So now that we know that zeros are good, if you can get a row or a column that has a lot of zeros, that's pretty good. If you can get a row or a columns that has a lot of zeros, that's good. Row 3 has a lot of zeros. I'm going to expand about row 3. And now I cross off column by column. When I cross off the first column, I get negative 1. This is the number that kind of got crossed off. It is in the third row, first column position. It is a 4. That's a 4. Times the determinant that remains. 1, 5, 1, 4. Now, I'll write it down again, but I'm hoping you see what's happening. So we elected to expand about row 3. Now, we crossed off column 1. Now, when I cross off column 2, and I hate crossing off things that have 1s because you don't see them. When I cross it off, the number that gets crossed out is a 0. That is, I'm going to have plus negative 1 to something plus something else times 0. That's something, those things, of course, is the third row, the second column, times a matrix. The matrix is going to be 2, 3, 5, 4. But the bottom line, since there's a 0 in that position, this whole thing's going to be 0. That is, and the same thing for when I cross off the third column. You pick a row, and then you cross off all 3 columns. Or you pick a column, and you cross off all 3 rows. But the thing with this one was, crossing off the third and the second column gave me 0. It's just a matter of crossing off the first column. That is, this is all I have to do. And this looks a lot less than the spaghetti method. This is 4. Negative 1 to a power, an integer power, will either be 1 or negative 1. Since 4 is even, it'll be 1. Times 4 is 4. Times this determinant, which is 1 times 4 minus 1 times 5. This is negative 1. 4 times negative 1 is negative 4. That wasn't bad. That was a lot better than the spaghetti method. If you can get a lot of zeros, it is excellent. I didn't argue why this method works, but it does. And assuming that you agree that this method works. If you have a row of zeros, well, pick that row, and any column you cross out, it's going to have a zero value. If a column has all zeros, pick that column. Okay. Suppose you have this. 2, 0, 1, 0, 1, 2, 0, 0, 0, 0, 4, 0, 1, 1, 1, 1. Now, I notice the third row has all zeros except one entry, and the fourth column has the same thing. The fourth column has all zeros except one entry. Since we haven't done a column 1 yet, let us pick this column. Now, the only entry in that column that's going to generate anything when I cross off the rows is the last row. Because when I cross off this row, there's a zero there. Remember, if you pick a column, you have to cross off the rows. When you cross off the second row, there's a zero there. When you cross off the third row, there's a zero there. The only one that's going to matter is when you cross off the fourth row. It's -1. This entry is in the fourth row, fourth column as well. Fourth row, fourth column. That entry is the 1, and the matrix that remains is a 3 by 3. 2, 0, 1, 1, 2, 0, 0, 0, 4. This is 8. -1 to the 8 is 8. Times 1 is 1. So this is 1 times that determinant is that determinant. Now, we could choose to do this spaghetti method here. But this section, cofactor expansion, we want to try not to do the spaghetti method. I noticed that the third row, it has all zeros except one entry. I like that. Let's expand around here. There's no need to cross off column 1 because there's a zero there. No need to cross off column 2. There's a zero there. That is, if you did cross off column 2. If you did cross off this column. So you have -1. This entry is in the third row, the second column. It's a 0. The determinant that remains is 2, 1, 1, 0. Now, this is some number times this number times this is some number. You're multiplying 3 numbers, okay? And one of them is 0. You're going to get a 0. There's no reason to work out what you get when you cross off column 2. It's column 3 that's going to be the only one that gives us any non-zero value. In fact, it may even give us 0. Maybe the determinant will end up to be the number 0. That is a possibility. The remaining determinant might end up being 0. So nonetheless, we cross off the third column. So the number that got crossed off, the 4, it is in the third row, the third column. It is a 4. And the matrix that remains is this. 2, 0, 1, 2. Now that matrix might end up being, that determinant might be 0. This is an even number, 6. -1 to the 6 is 1. Times 4 is 4. Times the determinant, which is 4 minus 0, which is 4. 4 times 4, 16. Minus some silly error, this determinant at the very beginning equals to the number 16. It equals to the number 16. So what happened is you start off with a 4 by 4, and then you end up with 3 3 by 3s. Why did we only end up with 1 3 by 3s? Because we knew the other two values were going to end up to be 0 anyways. So what we've noticed is having zeros is really, really good. If you can get a row or column to be all zeros, you're done because that determinant is 0. If you can get a row or column to have all zeros but one entry, then you only have to use cofactor expansion for that row. What do you mean, get a determinant to have this? Well, we have some theorems that talk about determinants. It says you can add a multiple of one row to another row, and the determinant doesn't change value. The determinant will not change value if you add a multiple of one row to another row. So suppose you have this matrix, this determinant. 1, 1, 2, 0. Pick nice numbers. 1, 0, 4, 1. 2, 0, 4, 1. And 1, 2, 3, 4. Suppose you want this determinant. Okay? Suppose you want this. Now, what you should do is look for rows and columns that have a number of zeros. And I noticed that column 2 has 2 zeros. So only row or column that has 2 zeros. Well, it'd be really nice if I can get that to be a 0. Because if that was a 0, I would expand about column 2 and only have to cross off row 1. Well, if I keep row 2 the same way, that is the 2 there. If I double row 1, there'll be a 2 here. And then I subtract. 2 minus 2 is 0. And then I can say these determinants are equal. Because now maybe I should write it this way. I took a multiple of row 1, and I'm adding it to row 2. That's exactly what that is. We can reword the theorem. You could add or subtract something. You can add or subtract a multiple of one row from another row. You could keep row 4, not row 2, excuse me. You can keep row 4 the same way, and then add or subtract a multiple of another row. And that is exactly what I'm going to do. As long as you keep the row you're changing the same. That is, don't write 2 row 4s, or don't write negative R4. Just R4. That's fine. So the first 3 rows are not being changed at all. 2, 0, 4, 1. And we're doing row 4. 1, 2, 3, 4. And we are doubling row 1. 2, 2, 4, 0. And then we subtract. Negative 1, 0, negative 1, 4. Negative 1, 0, negative 1, 4. And now, column 2 looks really nice. Even has a 1 for the non-zero entry. I'd rather multiply by 1 than 11, but nonetheless, having all zeros except 1 is wonderful. We are going to expand about column 2. That means, so let me write this 1 like that, so when I cross it out, it'll look better. You'll be able to see it, in other words. Okay, so I cross this out. Now, 1 by 1, since I crossed out a column, now 1 by 1 I have to cross off rows. But when you cross off row 4, there's a 0 there. You don't have to. When you cross off row 3, there'll be a 0 there. Don't bother. When you cross off row 2, there's a 0 there. So row 1 does not have a 0. So I cross off row 1. And what I get is those 3 pieces, -1 to that position. That 1 is in the first row, second column. So 1 plus 2. And then you write down the number that got crossed off. And then you write down the determinant that remains. Those 3 numbers were not crossed off. These 3 numbers were not crossed off. And then these 3 numbers were not crossed off. 1, 1, 4. This is 3. -1 to this 3 is -1. Times a 1, it's just -1. This is negative this determinant. How can you get rid of that negative in front? Well, you can interchange 2 rows. That will get rid of the negative. Okay, now, you can either use the spaghetti method or you can reduce some more. You could reduce some more. How about column 3 becomes, column 4. Because if I wanted to change column 3, I would have to do 4 times column 3 minus column 2. Because 4 times that would put 4 where those 1s are. But I can't multiply the column that I'm replacing by anything. So how about we go to column 2. Column 2 is going to become column 2, but then I'll take away 4 times column 3. Okay. So I have the negative in front. Column 1 is not changing. Column 3 is not changing, but column 2 is. It's column 2 minus 4 times column 3. 4 times those numbers are 4, 4, 16. 4 minus 4 is 0. 4 minus 4 is 0. 1 minus 16 is -17. Okay? 0, 0, -17. Let's get rid of our side work. Now, this 3 by 3 matrix, I don't have to do the spaghetti method on. I look at column 2, and I say, you know what? Oops, what just happened? I look at column 2, and I say, the only non-zero entry is in row 3. So I cross off row 3. And I get -1. This number that was crossed off twice is in the 3rd row, the 2nd column position. That number is a -17, and the remaining determinant is a 2 by 2. 1, 2, 1, 1. Oops. All right. Now, this is 5. -1 to the 5 is -1. -1 times -17 is 17, and the determinant is 1 minus 2, which is -1. And 17 times -1 is -17. You can use reduction rules to calculate this determinant. Now, to be honest, I actually worked this one out, and I got +17. So possibly there's a slight error somewhere. But the concept is key. You're able to do that. If you replace in row 4, just make sure it says row 4, not 3 row 4s. If you replace in column 2, make sure that says column 2, not 13 minus column 2. And make sure, if it says this, please realize that's negative C2 or negative 1 C2. It's not column 2. It's not column 2 then. If you want to multiply a column by something, that's okay. If you want to multiply by a row by some number, that's okay. But you somehow have to balance it out. I won't do this determinant to the very end, but I'll get rid of the fractions. Suppose you have 1/3, 2/3, 5/3, 2/5, 3/5, 4/5, 3/11, 2/11, negative 5/11. And you're asked to find this determinant. And you're like, you've got to be kidding me. You're going to find determinants with fractions? No, I don't. You can multiply the first row by 3. And you just get 1, 2, 5 for the first row. But wait a minute. And let's suppose I wrote down row 2 and 3. These determinants are not equal. Because when you multiply the first row by 3, this determinant is now 3 times the other determinant. So you know what? Why don't you put a third out front? You multiply by 3. By multiplying this row by 3, by multiplying the first row by 3, I multiply this whole mess by 3. So it no longer equals the other side. Well, I can counter that. I'll multiply by a third. I'm just going to need a little bit more space. So I multiply by a third. I multiply this matrix by 3. So it no longer equals the matrix on the left. But then when I multiply by a third, a third times 3 is 1. I only multiplied the right-hand side by 1. So it still equals the left-hand side. Now I'm going to play the same game with the second and third row. And multiply the second row by 5. And then multiply this row by 5. Oh, so the right-hand side now is 5 times bigger. No, it isn't. I'll multiply by a fifth. And I'll do the same with the third row. I'll multiply by 11. So then I have to counter that by multiplying by 1 over 11. I'd rather calculate the matrix on the right-hand side and then multiply it by 1 over 165. I didn't make a mistake. Those 3 numbers multiply out to 155. And I hope I didn't make a mistake multiplying the top numbers. It's 1. So you just find this matrix, this determinant, and whatever you get, let's suppose for argument's sake it's 11. Well, then the answer is 11 over 165, and 165 did come from 3 times 5 times 11, so the answer is 1 over 15. 3 times 5 is 15. That's if this equals 11. And I highly doubt that. Okay, so if you have fractions, you can get rid of them. You can get rid of the fractions. Same argument if you have decimal numbers. If you have decimal numbers, you can get rid of them. If somebody asked me to calculate the determinant of 0.1, 0.4, 0.04, 0.01, 0.3, 0.03, 0.1, 0.2, 0.3. In row 1, to get rid of the decimals, I have to move this decimal one place this one at least one place, and this one at least two places. 2's the winner. So when you move a decimal 2 places, that means you multiply by 100. So I have to multiply by the reciprocal. In the second row, I need to move this decimal at least 2 places, this 1, and this 2. 2's the winner. I have to move both decimals 2 places. And I hope you understand how I'm getting those numbers that I'm writing down. So I multiply 2 places, means I multiply by 100. You multiply this row by 100. I claim you get those numbers. But then you have to multiply by 1 over 100. And here, I need to move that one place, and that one place, and that decimal one place. So 1's the winner. And when you move a decimal one place, you multiply by 10. Well, then I have to counter that by multiplying by 1 over 10. Figuring out this determinant right here is much, much easier than figuring out this one, whether you use the spaghetti method or reduce. Okay. We'll do one more problem. I'll state a theorem, and what I'll probably do at the end of each section before I do the theoretical exercises is I'll update the list of non-singular equivalences. There's many, many ways to prove that a matrix has an inverse, and you don't have to prove it by finding the inverse. You can try to row reduce the matrix. And if you don't get the identity, you say it's singular. If you can't reduce it to the identity, you say it's singular. If you can reduce it to the identity, then you can say, yeah, it is non-singular. A inverse exists. All right. Suppose you wanted to calculate this determinant. Suppose you wanted to calculate this determinant. I noticed that column 1 and column 2 are almost the same. All but one entry in one of the rows are different. With respect to column 1 and 2, row 1 and row 2 are the same, and row 3 is different. So if I subtract, I'll have one non-zero entry. Suppose I say column 1 becomes, and I better write column 1, minus column 2. So column 1 is changing. Column 1 minus column 2. 3 minus 3 is 0. 5 minus 5 is 0. 3 minus 1 is 2. Column 2 does not change. Column 3 does not change. These two determinants are equal. One simple step, and now I have it down to a 2 by 2. I'm going to expand about column 1. It's the one that has the most zeros. And no point in crossing off row 1 because there's a 0 there in column 1. No point in crossing off column 2 because there's a 0 on the column that I am expanding about. But column 3 is different. So it's just going to be negative 1. This entry is in row 3, column 1 position. It is a 2. And after I cross off column 1 in row 3, those are the numbers left over. I put them down in the same order. And I have a 2 by 2 to calculate. This is 4. Negative 1 to the 4 is 1. Times 2 is 2. Times this determinant. 6 minus 5, which is 1. 2 times 1 is 2. That determinant at the top left, it equals the real number 2. So if somebody were to ask you, how much is 24 plus this. You know, tomorrow you won't know this answer. Maybe in an hour you won't know this answer. Me, I wouldn't know this answer immediately in 1 minute. But this answer is simply 26 because that's 24. And we just figured out that this is 2. And when I add 24 and 2, I get 26. That is, this is a real number. From now on, anytime you want for the rest of your life. I know you won't do this, but you can. From now on, instead of writing down the number 2, you can write down that determinant. They're equal. Just like you could always write down 5 minus 3. Okay, you can always write down 5 minus 3. You can also write down this 3 by 3 matrix. Here's this theorem that I promised that I'll give you. I almost forgot that I didn't. The determinant of A is not equal to 0 if and only if A is non-singular. The determinant of A is not 0 if and only if A is non-singular. Now, some logic. A if and only if B. Statement A, like determinant A is not 0, if and only if statement B. If you negate both of these, you can stick in if and only if. Try to make that neater looking, and I failed. The determinant of A is not equal to 0. If I negate that, if I say it is not the case that the determinant of A is not 0, the determinant of A the determinant of A does not equal 0 is false. I mean, there's only two choices. Either the determinant of A equals to 0 or the determinant of A is not 0. And I'm saying that's wrong. That's wrong. Oh. Or that's not true. That means the determinant of A is 0. If and only if I tell you that either A is non-singular or A is singular. There's no in between. And I tell you, I'm negating this. That is, this is not true. Oh, wait, you mean this is not true? Let me cross it off then. Oh, A is singular. If the determinant of A is 0, then A has no inverse. If A is non-singular, then the determinant of A is not 0. They come in pairs. They come in pairs. If the determinant of A is not equal to 0, that's the same as saying A is non-singular. Okay. So, it really wasn't, well, what I did do in this section, in my opinion, does not yield any theoretical exercises. But list of non-singular equivalences we just added one. This one right above. List of non-singular equivalences. The following list, the items on these lists, they all mean the same. They all mean the same. A is non-singular, and A is row equivalent to the identity. They mean the same thing. They both mean one thing. A has an inverse. If AX equals 0, has only the trivial solution, that means A is row equivalent to I. That means A is non-singular. AX equals B has a unique solution. That means AX equals 0 has only the trivial solution. That means A is row equivalent to I. And now, the determinant of A is not 0. If you find a matrix and the determinant of A is not 0, I guarantee you AX equals B has a unique solution. I bet you that A, for any B, I bet you that AX equals 0 has only the trivial solution. I bet you, or guarantee you, A is equivalent, is row equivalent to I. That means A can be reduced to the identity. You won't have a row of zeros. And if the determinant of A is not 0, I guarantee you A is non-singular. If A is non-singular, I guarantee you statement 2 is true. I guarantee you statement 3 is true. I guarantee you statement 2 and statement 4 are the same. If A is reducible to the identity matrix, then AX equals B has a unique solution. If AX equals B has a unique solution, I guarantee you A is row equivalent to the identity matrix. All these 5 statements are identical. They're the same statement. That is statement 1, if and only if statement 2. That is, statement 1 and statement 2 are exactly the same. 1 if and only if 3. 1 if and only if 4. 1 if and only if 5. 2 if and only if 1, which I already have. So if and only if 3. 2 if and only if 4. Statement 2 if and only if 5. Statement 3 if and only if 1, which I have. If and only if 2, which I have. If and only if 3, of course that's true. Only if 4. 3, if and only if 5. And then 4, I have 4 with 1, I have 4 with 2, I have 4 with 3. I only need to say 4 with 5. And 5, if and only if 1 is here, etc. If and only if 2, if and only if 3, if and only if 4. They're all equivalent. Any two are the same. They're exactly the same. Okay, that completes this section on cofactor expansion. Practice it. It's not such a bad technique, and you have to know well how to row reduce matrices, and then you could transform this determinant into a much easier one that has lots of zeros in a given column or a given row.